So in the last video, we were talking about linear regression, and we basically introduced the linear regression model and set up the problem as a maximum likelihood estimation problem for the regression coefficient beta. And then we obtained the maximum likelihood estimator, which is X transpose X inverse X transpose Y. Now, the question is that because there is an inverse of a matrix, we have to ask ourselves, when does that inverse exist? Okay. So what if X transpose X inverse does not exist? And that's very much possible if the matrix is singular. So the first answer to this question is, when does it exist? If X transpose X is singular, its inverse doesn't exist. Okay, so question now is, when is X transpose X singular? So there are two examples of when it could be singular. The first one is when the number of covariates or regressors or predictors, all meaning the same thing, P is more than the number of observations N. So when the columns of X are more than the rows in X, then what we have, I'm going to delete this, what we have is that X looks something, instead of looking something like this, where there are lots of rows and maybe a few columns, what it looks like is, it looks something like the following. It looks like this, where there are a few number of rows, but a lot of columns P. Okay. Now, the maximum possible rank of this matrix, okay, max rank of, that's not how I want to write that. The maximum rank of X in this case is just N, because it has to be the smaller of N and P. But X transpose X is a P by P matrix, right? So now the maximum rank of X transpose X is N, which we, by our assumption of the kind of X's we're looking at, is less than P, which means that X transpose X will be singular because there are some eigenvalues which will be zero. Okay. So if the number of observations over here is much less than the number of columns, then X transpose X inverse does not exist. Okay, that's basically what this is saying. So X transpose X becomes not full rank and cannot be inverted. And in this case, the MLE does not exist, right? Or cannot exist in the usual form at least. But basically, the idea is that other estimators need to be constructed. And this is one of the motivations of penalized regression. Now, there's another situation in which case X transpose X may not exist. And that happens even for tall observations when X is equal to something like this. But X itself is not full rank. So when rank of X is less than P, which means that there are some columns over here that are linearly independent, linearly dependent on other columns. So there's some linear dependence between this column, which means that there's a lot of correlation amongst the columns of X. That can also lead to X transpose X being not invertible. Okay, and this is one of the motivations of penalized regression. Okay. So here's the idea in penalized regression. Again, just to motivate why we're talking about these topics, even though this is a computing course, is we're setting up examples of where we will be needing computing. Okay, so one by one, we're setting up a few examples, and this should be the last video where we set up a few examples like this. Okay, so again, note that in the linear regression setup, the maximum likelihood estimate of beta satisfies that beta hat MLE is the argument that minimizes y minus x beta transpose y minus x beta. Now, If you don't recall this, let's go back to our beta hat MLE. The objective function was this over here, where both of these terms were not functions of beta at all. We only had this function of beta, this function of beta, where it gets maximized, doesn't depend on sigma squared. So in order to actually find the maxima of this term, I can just minimize this term over here inside. And so that's really what's going on, is beta hat MLE is the argument that minimizes y minus x beta transpose y minus x beta. Okay. So like motivated as before, suppose x is such that x transpose x is not invertible, right? Or even if it is invertible, we might look at penalized regression even out of that. But let's just assume x transpose x is not invertible. Then we don't know how to estimate beta. In such cases, we're going to be using penalized likelihood, where we're basically going to be penalizing the log likelihood in such a way that forces a certain behavior of the beta. So here's what I mean. The penalized likelihood penalizes the coefficients beta so that some of the betas are pushed towards zero. So let's imagine this situation again, where I have lots of columns. Okay. If I can somehow push the regression coefficients of any of these columns, some of these columns towards zero, then when I finally calculate the product x beta, then this just takes my fat matrix and multiplies with the corresponding beta vector, right? And if some of those are very close to zero, then the corresponding matrix products with them make that zero, right? So it basically negates the need for having that column. So if I push any of these towards zero that are not very large, so that there's some beta coefficients that are not very large, if I can push them towards zero, then I'm basically negating the need for that column, right? And for all of the columns associated with each of these things, right? And that's really one way of basically turning what might be a fat matrix to an effectively thin matrix. Now, it's not that these betas are going to be exactly zero, but they're going to be pushed towards zero. They could also be exactly zero, but that's the idea. Okay, the corresponding x's to those small betas, right? So the x's corresponding to those small betas are essentially not going to be important, right? So they're going to be effectively removed from the X matrix, removing the singularity from X transpose X, essentially. Okay. So in order to do this, instead of looking at the likelihood, we consider a penalized likelihood. Now, since the optimization of L beta given Y only depends on this term, what we do is we penalize the negative log likelihood. So this is going to be a little confusing, but I wanted to keep it the way it's usually done in the literature, is instead of penalizing the log likelihood, we take the negative log likelihood and we are going to add a penalty term next to it. Okay, so we take the negative log likelihood, right? And we're going to add a penalty term next to it. And so P beta is a penalization function. So our actual final function is Q beta instead of L beta given Y. We now have a new function of beta, that's Q beta. And this I want to now minimize, not maximize. I want to minimize this because I've taken a negative of the log likelihood. And once I've taken the negative of the log likelihood, I wanted to maximize the log likelihood, which means I want to minimize the negative log likelihood. So what does the penalty function do? The penalty function essentially assigns large values for large beta. So if beta is large, it basically adds a large penalty function, a large number to the actual object that I want to minimize. So if I want to minimize Q beta and P beta has added a large term to it, that large value of beta that adds this large P beta term, I don't want to choose as the actual minima. Okay, that's really the idea of what's going on. Okay, so so the optimization problem is basically going to favor large values. That's basically what's going to happen. Okay, another way to think about it is if I remove this penalty term and minimize the log likelihood, then this is going to be minimized at the MLE, minimized the negative log likelihood. Okay, so this is going to be minimized at the at whatever is the MLE. Okay? Now, if I take this term over here and just minimize this term, just the P beta term, then because this P beta term is typically going to be a term that's greater than zero, or greater than, let me say, it's typically going to be a term that's greater than equal to zero, then this P beta term is minimized for beta equal to zero. Right? So I have, on the one hand, if I only have this term, then I have beta MLE. And if I only have this term, then I have beta equal to zero as the ideal beta. So Q beta basically finds a balance between zero and the MLE. Okay, so we'll see an actual example of this. Now, what does P of beta look like? It could be any function really that's an increasing function of a positive increasing function of beta. And there are many penalty functions out there. The one that we're going to look at specifically in this video is the ridge penalty, but we'll also look at a different type of penalty in a few weeks. So there are many ways of penalizing beta, and one popular way is the ridge penalty. So let's look at the ridge regression. So just to highlight one thing, so I say ridge regression. The regression model is still the same, right? Which means my regression model is still y is equal to x beta plus epsilon. I only change the estimator of beta. And this is an important distinction. The idea in linear regression is that we want to understand what beta is. So one way to do that was to estimate beta using maximum likelihood estimation. But now I might have guessed beta to be all ones, right? Just without any information on the data, I might just guess beta to be all ones, right? And that also is a guess for beta. It's a very bad guess, but it's a guess for beta. It's an estimate of beta. Similarly, this ridge regression will give me another estimate of beta for the exact same model as before. So I can choose to estimate beta in multiple different ways. One of them is maximum likelihood estimation, and one of them is ridge regression. Okay, so ridge regression estimates are basically estimates of beta for the same regression model as we've studied. Okay, so for ridge regression, the penalty term P beta is lambda beta transpose beta by 2 for some lambda greater than 0. Okay, so Q beta takes then this form like this. Okay, so again, now if I call this is L beta and this is Q beta. Oh, sorry, not Q beta, P beta. Okay. So let's look at this again. If only L beta was there, right, then arg min of Q beta, or let me just not confuse this, of L beta is just beta hat MLE, right? It's just the maximum likelihood estimator. And if only P beta was there, then our argument that minimizes P beta, well, let's look at P beta. P beta is lambda by 2 beta transpose beta, which essentially this term over here is lambda by 2 summation j going from 1 to P beta j squared. Right? Which it takes all positive values. So the argument within beta in RP that minimizes P beta has to be the smallest value this can take is when all the betas are zero. So it is just the zero vector. Okay. So if only looking at L beta, I get maximum likelihood estimator. If only looking at P beta, I get zero as my estimate. So the solution to Q beta is basically going to be a balance between 0 and MLE. That's really what this is trying to do. Right? So our goal now is to minimize Q beta over the space of betas. And since we're adding an arbitrary term over here that depends on beta, smaller sizes or values of beta will be preferred. That's basically the idea. Okay. Further, the larger is the value of lambda, the more is the penalty. Right? So that means if lambda is large, then we're pushing for larger values or larger penalizations, which means it's pushing to zero more and more. Right? So lambda is typically chosen by the user, and we'll learn how to choose lambda again in the future when we cover topics like cross-validation. Okay, so now our objective is to find beta hat, which is the argument that minimizes y minus x beta transpose y minus x beta by 2 plus lambda by 2 beta transpose beta. Okay, now we'll carry out the minimization as before, but by taking the derivative. Now the derivative of the first term we've already taken before when we did linear regression. So that just becomes 1 by 2 on the outside, minus 2x transpose y plus 2x transpose x beta. Plus, by the same sort of rule that we took a derivative in the first expression, we see that lambda by 2 beta transpose beta is what I need to take the derivative of. This is essentially beta squared. So I get a 2 beta term left over. So 2 and 2 will get cancelled. So I just get lambda beta. I set that to 0. Now, once I set that to 0, and I solve this, this 2 gets cancelled with these things. And I see that there's a beta here and a beta here. So what I can do is I can couple this x transpose x beta plus lambda beta term. But x transpose x is a p by p matrix, and lambda is just one scalar quantity. So when I do pull this beta hat outside, this becomes x transpose x plus lambda IP. So lambda, notice, is only getting added to the diagonals of this matrix. Okay. I have a leftover minus x transpose y. So I set it to 0. I put this on this side and take an inverse of this over here. So I get beta hat ridge is x transpose x plus lambda IP inverse x transpose y. Now, in order for us to be convinced that this is in fact a positive, this is in fact where the ridge estimator happens, and this in fact is a minima, because remember we're trying to minimize. I want to check whether the Hessian is positive definite here. So stress on the term positive definite now, not negative definite, because now we're in a minimization problem. So over here, when I take a first, oops, that's what I want. Once I take the first derivative, I take another derivative to get the Hessian. So I get Hessian of Q beta is another derivative of this quantity here. But then there's only one beta term over here, so that becomes x transpose x plus lambda IP, whatever's constant next to the beta. This term doesn't depend on beta, so that makes it much easier. Okay? And I just get x transpose x plus lambda IP, sorry. Now, I need to show that this actually is positive definite, so that I know that it's a convex optimization problem. Now, x transpose x plus lambda IP is always positive definite, because as long as lambda is positive. So if lambda is positive, then if we take any A, which is an RP, right? If we take any vector that's a non-zero vector, and I look at A transpose the matrix A. So one way to check positive definiteness is if I have a matrix A is positive definite if A transpose, horrible notation, A small a transpose capital A, this thing is always greater than 0 for all A. For all A that's not 0. Okay. This is one way to check whether a matrix is positive definite or not. Now, typically it's challenging to check using this methodology because, you have to check this for all A that's non-zero. But sometimes it can be useful because once I multiply this, I get this to be equal to A transpose XA, so this term over here, plus lambda A transpose A greater than 0. Now, this is essentially a scalar quantity that's basically a sum of squares because it's just a square of two vectors, right? Transpose of, so this I can write as XA transpose XA, right? And this thing is already positive, right? Because this is also a positive quantity, and I'm assuming that lambda is positive. If lambda was 0, then this could go away, and then this need not be positive definite. But so now I'm sure that the Hessian is positive definite. So the objective function is indeed convex. Again, remember, I'm trying to minimize and not maximize here. And another thing that's really important is we were also inverting X transpose X plus lambda IP to get our ridge solution. And so because our X transpose X plus lambda IP is positive definite means that it has all positive eigenvalues, which means there are no zero eigenvalues, which means that I will always be able to invert this matrix. So it's always invertible, which is different from what we got in maximum likelihood estimation of the regression coefficient beta. Okay, so we can implement this as well. So now I just choose lambda equal to 2 for the cars data set. Okay, and when I choose lambda equal to 2, with that beta dot hat, which now is my ridge beta, is the solve of, so the inverse of X transpose X plus lambda IP. P in this case is just 2 because I have the intercept and the slope, right? Times X transpose Y, right? And this turns out to be minus 12.6 and 3.64. Now let's take a second to see what the estimate was here. So it was minus 17.6 and 3.93. So this thing corresponds to, in the MLE estimates, was minus 17.6 and 3.93. Notice that both of these numbers are now closer to 0, right? So if this is the real line, and I have minus 17 here, and I have 3.93 here, then my rich estimates are, negative 12, closer to 0, this is 0, and 3.6, which is again closer to 0. So I'm shrinking my regression coefficients towards 0 using the lambda penalty. Okay, and similarly, I can also calculate sigma squared by the usual method of y minus x beta transpose y minus x beta by the sample mean, divided by the length of the sample, sorry. That's the usual method that will remain in this case as well, right? So moral of the story is if X transpose X is not invertible, we can still implement ridge regression to get another type of estimator of the regression coefficient that also works fairly well and looks all right to us as well. Okay. Now, what are the pros and cons of ridge regression? So first of all, we have an estimate of beta. If we can't invert X transpose X, we may not have an estimate. So this gives us a way to get an estimate. And as we'll see a little later on in the course, is in terms of certain criteria, we actually do better than non-penalized estimation, even when X transpose X is invertible. So if even when this is invertible and we could do maximum likelihood estimation, we actually there are problems when ridge regression might to give us better estimates than maximum likelihood estimates. Okay, and we'll discuss these as well. So what are the cons? So the cons are mainly that the estimator is not an MLE. Now, because it's not an MLE, we discussed MLEs have very nice theoretical properties, right? They have consistency and they have this asymptotic normality, and those are not properties that follow for ridge estimates anymore because um, we don't have those nice MLE properties. So that can be a problem. And this can be addressed by bootstrapping, which is again something we'll learn in the course. And this is why it was important to sort of go through these topics, right? And we'll also do one more type of penalty later on in the course. Okay. So here's some questions to think about. So under the normal likelihood, I think it would be a really good exercise to understand what the distribution of beta hat MLE looks like when it does exist. So beta hat MLE is also a random quantity that's coming from random data. It has a distribution as well, and it's I don't want to say fairly easy, but it can be shown that it has a certain distribution. So try and see if you can find the distribution of beta hat MLE, and try and also see if you can find the distribution of beta hat ridge. And are both of these unbiased or biased? And which one do you think has a smaller variance? That's something that would be a great exercise for you to try out. And I discussed what type of properties should penalty functions have. P of beta should be an increasing function of beta and should be essentially greater or greater than equal to 0. Okay, so what other types of penalty functions can you think of? One of them is recall that beta transpose beta is the L2 penalty or the L2 norm. And so what other functions can you think of?